Good. Okay. All right. So let's get started. So today we will talk about fault tolerance. We started that topic last time, if you remember. Last 15 minutes of the class, I introduced what is fault tolerance, why do we need it, and so on. So today we will look at many different ways to implement fault tolerance in distributed systems. We look at essentially the problem of how do processes agree on some computation when there is a fault. We'll look at what is called the Byzantine generals problem, which is going to address this whole issue of Byzantine fault tolerance. I'll explain what that is. We will have a brief recap of how to deal with failures from the network perspective. We had talked about some of this when we did the class on remote procedure call. So I will recap some of that and have some new ideas there. And then we will end with this problem of distributed commit, okay? Which again I'll introduce. We'll probably do the two-phase commit today. Depending on time, we may or may not get to the three-phase. Okay? But that's really the three things we are going to talk about today. So let's skip a few of these slides that we already discussed last time and get to this notion of agreement in faulty system. Okay? So the picture you want to keep in mind here is you have a system with n processes, okay, a distributed system, and they need to agree on some computation that they're performing. Maybe they send a request and you want to make sure that the response that comes back is correct, and you want to do this in the presence of some of these nodes failing. Okay? Remember last time I talked about two types of fault tolerance that we will actually look at. One is called crash fault tolerance, okay, which means that a process can either work normally and produce correct result, or it fails, and it fails by crashing. And once it's crashed, it produces no output. Okay? It basically stops responding because the process just crashed. Okay? So in this case, either if the process is up, it's assumed to be correct, and if the process is down, it's not working at all. It just stopped responding. Okay? So this is called crash fault tolerance. And then the other type of fault tolerance we are going to talk about is called Byzantine fault tolerance. And in Byzantine fault tolerance, processes continue to run even when they are faulty, but they can produce arbitrary results. Okay? Byzantine faults can occur because of bad bugs in your code, or maybe the software got hacked, and then there is now adversary who is controlling the software or the process application, and it can start producing arbitrary results. Okay? So these are the two types of fault tolerance that we look at. Let's start with crash fault tolerance. Okay? Crash fault tolerance simply says that a process either works and it is up, it produces the right result, or it crashes. So how can you make a system fault tolerant to crashes? I mean, so you basically create replicas. So you will have some number of replicas, so that even if the other replicas crash, the ones that are up can continue to produce results. Okay? So this gets us to the notion of a k fault tolerant system is any system that can tolerate k concurrent faults and yet continue to function. Okay? So one fault tolerance means one process crashes and it still continues to run. Two fault tolerance means two of the replicas, okay, that you have crash simultaneously. And so you can have any number of replicas that might fail, and depending on how robust you want to make your system, you can design it to be k fault tolerant, where k is any number, any integer that you can pick. Okay? So the basic idea is when you have crash fault tolerance, okay, you are going to essentially have k plus 1 replicas, okay, to tolerate k faults, because you have k of these replicas failing, okay, and you want at least one that works. Okay? Because as I said, if the crash fault tolerance, if the process is working or the replica is working, it's producing correct results. Okay? So if you have processes that fail silently, which is another way of saying this crash fault tolerance, you need k plus 1 redundancy to tolerate k faults. You need k plus 1 replica to tolerate k faults. Okay? So if so long as at least one process is up or one replica is up, you can produce results. Okay? That's a very straightforward thing. So if k is equal to 1, okay, that means that you have to have two copies running, okay? So that if one of them crashes, the other one takes over. That's the most simplest case you will see in many systems. Okay? Typically, you can have k greater than 1, but k equal to 1 is a common case. So you want to have one fault tolerant system, which means one fault can occur or one failure can occur. Okay? Now let's take the other case, which is Byzantine fault tolerance. Okay? In Byzantine fault tolerance, processes can continue to run even if they are faulty. Okay? So now if you want to tolerate k faults, okay, it's not adequate to just have k plus 1 replicas, because you don't know whether a process is faulty or not. In crash fault tolerance, you know a process is not working because it has crashed, okay, not producing output. Okay, so in Byzantine fault tolerance, all the processes seem up. They're all producing output when you send them a request. So you can't tell whether a process is faulty or not just because it's up and running. Okay? So we need an additional degree of redundancy, as we will see, and we'll have to ask that question: how many additional replicas do you need to tolerate k Byzantine fault? To tolerate k crash faults, you just need k plus 1. To tolerate k Byzantine faults, you need a lot more, as we will see, because these types of failures are difficult to actually detect and overcome. Okay? So you might just have processes that are producing incorrect result to confuse the system. Okay? So let's now talk about Byzantine faults. Okay? We'll talk about several different scenarios. Okay? The first scenario is where the network is the part of the system that is faulty. The processes are actually fine. Okay? So what does that mean? Process A in a distributed application sending a message to process B, we can assume that the network can do arbitrary things to the message. It can drop the message, never deliver it, or it can actually change the message and deliver a bad message. Okay, so you might send one RPC request, but the request might be changed by the network and essentially something else actually arrives at the other end. So in some sense, there's an adversary that is sitting in the network, can intercept messages, change them, and so on. Okay? So then the question is, how do you actually overcome this type of faults? Okay? We'll analyze this with a very simple scenario where you have two processes, okay, and a network between them. Okay? And these two processes are simply sending a 1 bit across one another. So they can either send a 0 or a 1. Okay? So it's a 1-bit message. It's the most simple message that you can send. Okay? And the question is, can they both agree on what the message is that was sent, and they know that the message was sent successfully? Okay? And we'll assume the network, as in this case, is Byzantine faulty, so it can do anything. It can take a message, not deliver it. Okay? It can take a message that is 0 and turn it into 1 and deliver a 1. Or it can take a message that's 1, deliver a 0. Or it can deliver the message exactly as is without doing anything. Okay? So at any time, it can do any arbitrary thing it needs. So it wants to do, and you still want to communicate in a reliable manner. Okay? Is this clear what we are trying to do? Okay? So in this case, network is faulty. The processes are fine. And the question is, can we actually reach agreement? Which means agreement basically means both processes know this was the message that was sent and the message was delivered successfully, that the network did not do something bad to the message. Okay? So we will take this problem and try to actually conceptualize it in terms of what is called a two generals problem. Okay? So here we are assuming a scenario where there are two armies trying to attack one another. Sorry, not attack one another. Two armies trying to attack a common enemy, so they want to coordinate, okay, what time it is that they should launch an attack. Okay, and the assumption is the way they are going to coordinate is they are going to send a messenger back and forth to actually try to decide what is the time that they want to attack. Yes, you have a question. Okay, so we'll, yeah, okay, okay, so that's a good point, which is the network is the issue. Can you not use cryptography and so on, right? You can use cryptography, but you can't deal with a network that doesn't deliver messages at all, right? So you can, because anything can happen. Network can just say it'll drop messages. So we'll try to understand what you just said. in the more simpler way without any cryptography. Okay, so two armies are waiting to attack a common enemy. They want to coordinate the time of the attack, and they are going to essentially send a messenger back and forth. Okay, and the messenger has to go through hostile territory. Okay, so you send a messenger saying, let's attack tomorrow at 9 a.m. You don't know whether the message was delivered because the messenger could be caught. Okay, while they're trying to deliver the message, the messenger could be caught, and a different messenger who's trying to masquerade as the original messenger might deliver a fake message. So you don't know what is going to happen. Okay, you just send a messenger out. Okay, you don't know whether the message was received and things like that. But you need to reach agreement. Okay, the agreement here means you need to know that your message was actually received at the other end and received successfully. Okay, the question is, how are we going to actually do this? Yeah, let's say we'll call them army A and B. A sends a message to B saying, let's attack at a certain time. Okay, let's say for sake of argument that the messenger actually went and delivered the message. The message was not lost. Okay, now the question is, does that mean we solved the problem? Okay, and the two armies now decide that they have actually agreed on what time to attack. Okay, I'm just saying there's no message loss, there's no change of message. The messenger just made it to the other end. Does that address the problem? No. Why not?
The other process also has to agree.
Okay. The other process to agree. Let's say the other process says fine. Right? It's fine as in it will take whatever time came and say, let's do it. Okay, so let's not worry about that because processes are actually operating without any faults here. Okay. So the question that you should ask is, how does A know that the message was actually received? A just sent a messenger. I just told you that the message actually reached, but how does A know that the message reached and it can actually go ahead and launch an attack at whatever the time is? Okay, so A doesn't know whether the messenger was intercepted, okay, or received or delivered the message. So what can we do? Okay, we'll copy TCP and then we'll do what? Okay, so what can you do? You can send an acknowledgement. You can basically tell the messenger saying, go back and say that you delivered the message successfully. That's an ACK. Okay, so let's assume, again for sake of argument, that the message actually comes back, the messenger rather, comes back successfully and said, I went and delivered the message and I want to come back and say that, that I did that successfully. Okay, so now you sent a message, you got an acknowledgement. Are we done now or did we solve the problem? And the two generals say, yes, we can now launch an attack. Yes. So the point is now, how does the second army know that the ACK was received? Because it has to know that the ACK was received, otherwise it can't launch an attack because you don't know that the other army now knows that you got the message and the ACK was received. Okay, so now what? You will send an ACK to the ACK. Can we not multicast an acknowledgement to from the messenger? What does that mean? I mean, think of a real scenario, right? The messenger can only go back and forth. So it's similar to that, right? Can't do a multicast. So you can send an acknowledgement to the acknowledgement. The messenger can go all the way back saying, I deliver the message that I delivered was acknowledged, and I'm sending an ACK to that. Okay, but that problem is never going to go away because you never know whether your original message was received or the ACK was received or the ACK to the ACK was received, because you'll have to just continue recursively sending ACKs to ACKs and ACKs to ACKs to ACKs and never actually get to a point where both parties know that we have now agreement on what to do. Okay, is that clear what I just said? So what this is saying is a very simple property which says that two perfect processes cannot reach agreement if the channel is unreliable. Okay, so this, in some sense, this problem cannot actually be solved. You cannot reach agreement if the network is problem. Okay, the processes are fine. Okay, so that's basically an impossibility result. And I just gave you a very simple example of why you cannot. And the point is, what you want to do is the agreement here means you want to get to what is called common knowledge. Common knowledge essentially means that you know something and you know that everyone else knows that same thing. Okay? And everybody else also knows the same. Okay? That means that it's now common knowledge, and you cannot reach common knowledge because every time you're trying to send a message or send an acknowledgement, there's always a chance that that message does not reach. Okay? So you actually never get to a point where you have common knowledge. Okay? So this problem we cannot solve. Okay? The network is the problem, is a hard issue. You cannot actually deal with this. Okay? Even cryptography, as you were saying, doesn't help because this is an acknowledgement issue. Right? You cannot actually figure out whether the message even got there or the act got there. Correct. So now we want, yes, your question. Okay. Question is, why are two acts not sufficient in the two generals problem? First thing is TCP has only one act, not two. And you send a message, you get an acknowledgement. Okay. Even if you have a version where you send an act to the act, you have to think recursively, right? So if you just think about this problem that I was explaining, okay, two armies are trying to get agreement, okay, on whether to launch an attack. You first send a message, okay, and you need to know whether the message was successfully received. So only then you can launch an attack. Otherwise, you don't know. If the message was not received and you launch the attack, then the other army is not going to launch the attack, right? So then your coordination didn't go. So you have to wait for an acknowledgement to come back so that you know that the message was successfully received. When the act is successfully received, what you know is that the message went there and it came and you got an act. So you know the other party knows. So you can launch the attack. But the other party does not know whether you got the act. So they can't launch the attack because if the act was not delivered and they launch the attack, then the other party won't. So you can reason this recursively and you will see you'll never reach agreement. Okay? That's the problem. We in TCP, we are not trying to reach agreement. We just want to know if the message was received successfully, but it's not the problem of you're trying to coordinate something. Okay? We just want to know if the message was delivered or not, an act is adequate. Okay? Here we are trying to actually reach agreement, which is not the same problem as did the message get delivered. Right? Okay. So that's the two generals problem. Now we will try to solve a different problem. So in this case, we will assume that the network is reliable. There's no problem. Okay? We'll assume that you can use TCP or whatever we want. The network is not the problem, but one of the processes is actually faulty. This is the problem that we were trying to address. So you have n replicas. Okay? In this case, we'll assume one replica is faulty. Okay? You don't know which one. Okay? So this is now, there are n generals. Okay? And we'll assume that in this case, one general is a traitor. Okay? They are trying to confuse. So the n generals are trying to reach agreement on when to launch an attack. There's one general that's a traitor. What the general can do arbitrary things. They can send wrong messages. They can send the right message. They can send different messages to different generals and cause confusion. Okay? And here we want to see, can we reach agreement on when to launch the attack? If some subset are faulty, we'll start with an example of one. But in general, the general problem is m out of n may be traitors or faulty. Okay? So traitor is exactly what a Byzantine fault is. Okay? They can do arbitrarily malicious things just to confuse every other process. Okay? Like unlike a crash process where you don't send any messages, a traitor process or a Byzantine faulty process can send arbitrary messages. Right? And yet we want to reach agreement. Is the problem clear? We'll see how to solve it. Okay? Here's the example. We'll start with a case where there are four generals, which we'll call 1, 2, 3, and 4. There are four processes. Okay? We know that 3 is the faulty process. Okay? But the generals don't know that. Okay? Because they just are receiving messages. They don't know that there is a traitor or who the traitor is. Okay? And we got to figure out, reach agreement and try to isolate the traitor. Yes, so this is going to be a recursive algorithm in Lamport's. Okay? So here is how it's going to work. Okay? Each general is going to send a message. Okay? What you are trying to reach agreement on is not an issue. You can try to agree on what time to launch an attack, or what you can agree on how many soldiers each of the generals have. Okay? So So that's really not the problem of what you're trying to reach agreement. The question is how to reach agreement. So in this example, we are assuming that traitors are not traitors, generals are trying to tell others, even in the presence of traitors, what their army strength is. Okay? But it could be anything. You could have said, this is the time you want to attack or something. So we'll have a 2-round process to figure this out. In round 1, each process is going to broadcast its strength to other generals. So you will say, okay, so in this case, General 1 is going to say, I have 1 soldier. It doesn't matter how many soldiers there. So you'll say, I have 1 soldier. You send that message to everyone. Okay? General 2 sends a message saying, I have 2 soldiers. Okay? General 3 is the faulty process. It can send arbitrary messages. So we'll just say it sends X to 1, Y to 2, and Z to 4, which are arbitrary integers. They could be the same integer. They could be different integers. We don't know what it's trying to do. So we'll assume it sends arbitrary message. Okay? X, Y, and Z are variables that can take any values. They can be equal. It might confuse things by actually sending a valid message, an invalid message, different messages. So it can do whatever it is. Okay? And 4 is going to send 4 to all the other children. Okay? So at the end of round 1, okay, what is shown in B is the messages that you have received. Okay? So 1 will have gotten 1 because it knows what it does. 1 from itself, 2 from 2, Y from X from 3, and 4 from 4. Okay? And 2 would have gotten 1, 2, Y, 4. 3 would have gotten the right things because it knows what it has. And 4 got 1, 2, Z, and 4. Okay? So that is the information each of the general has. Okay? They don't know which of this is correct information, which of this is incorrect information. This is just what you received from the other generals. Okay? Now you got to figure out, okay, is there a traitor and who it is. Okay? So what will you do? You will take whatever messages you received, okay, and you will broadcast it back, saying this is what I got in the previous round. Is that clear? What I just said? So you will basically send 1 to X and 4, and 2 will send 1 to Y4, and so on. 3 can again send confusing messages. So it may send A, B, C, D to 1, and it may say E, F, G, H to someone else, and whatever it wants to the third one. Okay? So after the second round, this is what each of them would have received. So 1 would have gotten 1 to Y4 from 2. It would have gotten A, B, C, D from 3. It would have gotten 1 to Z4 from 3. Okay? And so on. Okay? So now if you look at these messages, what does that tell you? Okay? You can isolate which are the rows and columns that don't match. Okay? You will see that the row column from 3 is not matching because it may have sent different things, and then it could have sent A, B, C, D. So you will know that 3 is trying to confuse matters because it's sending wrong messages to everyone else, and others have now reported the messages they've received. So you can identify which is the faulty process, okay, and then essentially ignore what it's saying and try to reach agreement on the rest. Yes, question. Question is, what is it that you're sending in round 2, if I were to summarize the question? So you send all the information you received from every process in the previous round, you're broadcasting. Everything, not just what you sent. So if you will send 1 to X4, like 1, that's the message that 1 is going to send. Okay? 2 is going to send 1 to Y4 to everyone, to every other process. Okay? Which is why in round 2, you basically get what everyone received in the previous round. Okay, so the first round you are getting a single integer. The second round you are getting a vector with 4 values. Okay? Is this clear? Okay, so in 2 rounds, in this case, in 2 rounds, we were able to identify a traitor and we were able to reach agreement because other processes are reporting the right values. Yes, your question. So you're saying if there are 2 faulty processes? Yeah, okay. So okay, so question is, what happens if there are 2 faulty processes? Okay, so this only works if there's 1 faulty process. If you want to deal with 2 faults, you will need more replicas. Okay? So as you will see, what I'm going to show you on the next slide, not next slide, but I'll show you another example. Then we'll generalize this to see how many replicas do you need to tolerate K faults. Okay? Here K was 1. If you have 2 faulty processes, you will never reach agreement because there will be multiple rows and columns that don't match. You don't know what is happening. Okay? You will not understand who is reporting the right value, who not reporting the right. Yes. Yeah. Okay. Question is, can the faulty process send same incorrect message, right? So if you send the same incorrect message, you are acting like a normal process in this case. So you will actually not be identified, nor will you be isolated. Okay? But that's okay, because you could think about this as to answer your question. Let's say you're not actually broadcasting the strength of your army, but you're doing a computation. Let's say you are running the add process. Okay? And all the processes have been asked to add 2 plus 2 and try to arrive at the answer. Okay. So now you are basically broadcasting the result of your add function as opposed to this. So you will basically send 2 to x4, right? X2 and so on. So in this case, if the faulty process sends 2 plus 2 is 4 to everyone, that's okay. It sent the correct message, doesn't it? But if you say 2 plus 2 is 5, okay, the others will say 2 plus 2 is 4. So you have 3 processes agreeing that 2 plus 2 is 4 and one is sending 5. And you can still figure out that it's actually incorrect, even though it sent the same wrong message to others. Okay? So depending on what you're trying to do, you can actually send the same incorrect message and still get idea. If you send the same correct message, then it's okay. So then you perform the computation correctly. Is this clear? Any questions here? Okay. So we'll repeat the same problem now, but we'll assume that there are only 3 generals, not 4. Okay? And 3 is still the faulty process. Okay? So what happens in this case? The same example, right? So the first round, 1 is going to send 1 to everyone, 2 sends 2, and 3 is sending x and y. Okay? So you are basically going to get 1 to x, 1 to y, 1 to 3. Okay? And then you are going to recurse, and you are going to send this out, and you will have in the next round you got 1 to y, a, b, c from 3, and 2 got 1 to x, d, e, f. 3 gets whatever it gets. Right? So now you see that the message that each correct general, which is 1 and 2, you will see that it's getting 2 different messages. Okay? It gets something from 2, like 1 is getting something from 2 and something else from 3. They don't match. Okay? Because 1 to y may not match with a, b, c if 2 has sent arbitrary values, substitute arbitrary integers. Okay? So you know that there is a faulty process that's sending bad messages, but you don't know which one is faulty. So you can't actually isolate in this case. You can detect that there is a fault, but you can't isolate the faulty process and ignore it, which you could do, and there was one more process in the previous example. Is this clear? Okay. So it is very similar to you have 2 friends, you ask them for some information, okay? One of them lies to you. Okay? So their answers don't match, but you don't know who is lying because you don't have any other information to figure out, okay, whom to believe or not to believe. Okay? But you have 3 friends and you ask them the same question and one of them lies, the other 2 are going to say the truth, and then the third person, the liar, gets isolated. It is the same problem. Okay? Here, so each general needs actually 3 other processes, one of whom is the traitor, to make sure you can isolate the traitor. If you only have 2 other processes, they produce 2 different responses. You can't figure out which one is correct and agree with that one. Okay? Is this clear? Yes.
Just send one message. Send a string, arbitrary string that every arbitrary string is a faulty process. It will send any other strings. One round will be able to.
So you are saying you can send a string, then what happens? I don't understand what you're saying. Right. So this is a protocol that should work for any arbitrary thing. So you can say this could be a database, right? The generals are databases. You are sending a query. Okay? One of the databases is faulty and it produces garbage results for the query, right? And then you want to figure out which is the bad one and try to isolate. Or it could be a web service where you're sending requests. One of them is faulty, it's sending bad responses. Okay? So it could be any scenario, you still want this protocol to work. Okay? In this case, we were just having using a very simple example of an army and so on. But in reality, this is a distributed system where the processes are replicas that are performing an arbitrary computation. One of them is faulty. You have to figure out which one and isolate it and still have the system continue to run. That's the goal, right? So maybe the very special case you mentioned might work, but this has to work in the general case. Your question is?
Yes. Why not use the data that one got had, for example, in one got, it looks like one got 1, 2x, and then 1, 1 is larger, is like more than an a, and then 1 is a line.
So I didn't understand what you're saying. So you said you can take what you got and compare it with 2? Yes. 2's response?
Yes, like one got 1, 2x.
Yes.
And then we can put it in another row of one got and compare it to a. Then we got 2 1s and 1 a. So a is like.
No, I don't think it still work actually, because it's same problem as, because you're trying, remember, you're trying to reach agreement. So you are basically trying to say, what is it that you should agree on? If you have one process that disagrees with the other one, you don't have it. Okay? So it's not going to work actually. You can detect that there is a problem because there is no agreement, not agreement, there's no match between the responses, but you can't figure out which of the two to believe in this case.
But one got 1.
One got 1 to x, yes, in the first round.
Then one got 1 to y. Got a.
Yes, yes.
Then we have 2 1, 1 a.
Still don't understand how that actually helps figure out who is the faulty process, right? Because you are assuming that everybody else also has to agree on the same thing, right? So you have to assume that that process may also be faulty in some case, right? So it will not actually get you what you are saying. Okay, maybe we can talk after class so that you can explain what you're saying a little more. But the property here that you want to keep in mind is, if there are m faulty processes, okay, agreement is possible only if there's a greater than 2/3 majority. Okay, so you want 2m plus 1 processes to be working correctly out of 3m plus 1. So in other words, the other way to say this is, if you want to tolerate m Byzantine faults, you need 3m plus 1 replicas. Okay, when m was 1, okay, you need 4 replicas, okay, which is what we had in the previous case. Okay, so essentially of those 4, there's 1 faulty and 3 correct. If m is 2, okay, you will need 7 replicas to solve the same problem, because you have to now isolate 2 faulty processes, okay, out of, in this case, 7. Okay, so essentially the degree of replication is at least 3m plus 1, okay, which is a very high cost if you can think about this. So to tolerate 1 fault, you have 4 times the cost. You'll have 4 servers running, 4 replicas running just to tolerate 1 fault. In crash fault tolerance, you want to tolerate 1 fault, you need 2 replicas, right? So the one fails, the other one works. In Byzantine faults, you want to tolerate 1 fault, 4 replicas, okay? 4x cost, okay? Which is a very high price to pay. Okay, most real systems will not want to pay such a high cost, so they may not actually be able to deal with Byzantine fault tolerance. Okay? Except things like blockchains and so on that want consensus even in the presence of Byzantine fault. So you want Byzantine consensus and things of that sort, you will pay that high price. But other systems like web servers or things like that, they often deal with crash fault tolerance, but not Byzantine fault tolerance. Okay? So you need more than 2/3 processes to work correctly to actually get this property. Okay? So that's a high price to pay. Okay? So this is what I was saying in this, what I just said is actually reflected in this slide, saying detecting crash faults much easier. Okay? K plus 1. Detecting that there is a Byzantine fault, okay? 2k plus 1, okay? Which is this. That's just detecting, not isolating. So you know that there is a fault because there's no agreement. Okay? You can't figure out what is right and what is wrong. Okay, and then reaching agreement after detect requires 3K plus. Okay, so essentially you need 2/3 majority to eliminate the faulty remote. So you have crash fault tolerance K plus 1. Okay, in Byzantine fault, just to detect that there is a fault, 2K plus 1. So if you want to detect and recover, you need 3K plus. Okay, so there's a lot of replication that you have to do in order to deal with Byzantine. Is this clear? Okay. All right. So, and we already said if the network is faulty, okay, that's a bigger problem that we can't even deal with. So if the same thing you can say if the network is actually not necessarily faulty but slow, okay, you still have a problem. Okay? Because if the network is slow, you cannot distinguish between a failed process and a very slow process. Okay? You send a message, it takes an arbitrarily long time for a reply to come back because the network is arbitrarily slow. You don't know if the process actually failed and hence the response hasn't come back or the network is just. Okay? So when there are network issues, I think this problem gets even harder because you cannot distinguish slow processes from faulty. Okay? So Byzantine fault tolerance has been an area of research for a long time, and because there is a very high cost, there have been all kinds of techniques that people have come up with. Then can you reduce that overhead? That's a fundamental limit. But if you make certain assumptions, you can relax that 3K plus 1 bound. So for example, if you say only some of the nodes are Byzantine, but others are collaborative, you trust some nodes more than others, maybe you can reduce the cost and things of that sort. But you need to make additional assumption. If you assume that any node can be faulty, then you're stuck with the 3M plus 1. Okay? And this area has now again gotten a lot of attention once things like blockchain became popular. Because in blockchains, you actually need to reach Byzantine consensus because there are arbitrary processes that are mining whatever cryptocurrencies and participating in a consensus protocol. You can assume that there are people willing to do bad things. Okay? So you want to reach consensus even if some subset of the nodes are actually doing arbitrarily bad things. So all of these protocols in the past 5 or 8, 10 years have again become really popular in terms of how do you reduce the cost and what assumptions to make and so on. Is this clear now? Okay. So that is what I wanted to say on Byzantine fault tolerance. We'll come back to some of this when we come to consensus, okay, maybe next class. But what I want to do today is to just do a recap, a one-slide recap of something we discussed back in lecture 3, okay, which was reliable one-to-one communication. When we were talking about remote procedure calls, you remember we said how do you have reliable RPC even in the presence of various kinds of faults where the client may have failed, the server may have failed, the request or the network didn't get delivered, the response did not get delivered. And we looked at various approaches to deal with those types of faults. And those were all crash faults in some sense. Either the network crashed or not crashed. The network just failed to deliver a message, okay, or the server crashed or the client crashed. We didn't need to reach agreement or anything like that. We just needed to make sure a response comes back. Much simpler problem to deal with. Okay? But just keep that in mind what we talked about at that time. A lot of this we could deal with TCP because TCP takes care of the networking problem. Okay? It will retransmit packets until they are received and you get an acknowledgement, so you don't need to deal with it. Okay? But if you now have many-to-one communication, okay, then you have a slightly different problem. So this is many-to-one communication is called multicast. In multicast, you have one sender, multiple receivers. You make a send and multiple nodes receive it. Okay? So here we now want to ask the question, what can we do if there are lost messages? Okay? You send a message, it has to go to n receivers, or only some subset of them get. Okay? Just as TCP has a timeout, if you don't get an acknowledgement, you time out and retransmit, you will need some form of retransmission scheme. Okay? So the simplest extension you can make, okay, in this case is to say, when I send a multicast a message, each receiver should send me an ACK. Okay? So I send a message, it gets to n receivers. All of them need to send an acknowledgement to me, so I know that everyone received. Okay? That's the same as TCP. There's only two entities there. You send a message, you get an ACK to make sure the other party receives. Okay? So you could just have an ACK-based scheme, okay, for multicast. But in an ACK-based scheme, okay, what can happen is you will actually have a bottleneck at the sender as the size of the group increases. And that is the example that's actually shown here, okay, where this is the sender node. Okay, there are 4 receiver nodes. Okay, and the sender has sent message number 25. Okay, M25 is message number 25 to all of the receivers. Okay, and then you are waiting for acknowledgement. Okay, so in this case, if you have n members in the group, you will receive n acknowledgements. Okay, but n can be arbitrary. Okay, n could be 10,000. You may be sending a multicast message to 10,000 receivers. So for every message you send, you get 10,000 ACKs back in this case. Okay? So that increases the overhead of ACK processing on the sender, because the sender has to track every receiver saying who has received it, who has not received it, and then either time out and send a request and so on. Okay? So not send a request, but retransmit the request and so on. Okay? So this is called the ACK explosion problem. Okay? So as the size of the multicast group grows, simple ACK-based scheme that work really well in TCP don't really work well if you're just trying to get reliability for multicast, because you will get a lot of ACKs. Okay? So what people have done is they have essentially a different approach, which is called a NAC-based scheme. NAC stands for a negative acknowledgement. Okay? What's a negative acknowledgement? It's basically the opposite of an acknowledgement. You send a NAC only if you know you did not get something. Okay? If you receive messages, you don't send anything. Okay? If you miss a message, you are going to send something. Okay? What does that even mean? Okay, let's take the same example. Let's say that the messages you are sending are numbered. Okay, so you not only send the message, but you actually have a sequence number on them. So you know which message you received. So in this example here, okay, every receiver has received all the messages through message number 24. So that's why the last equal to 24. Okay, the sender is trying to send message number 25. Okay, so 25 gets to all the receivers successfully. Okay, but there is one receiver that had not received 24. So its last was 23. You will see here. Okay, the others received 24. So when message number 25 arrives at the receiver, it will say the last message I received is 23. Now I got 25, so I missed a message. Okay, so you're going to send a NAC for that message saying, yes, so you will see now that is sending out a NAC saying I need message 24. Okay, the NAC can only go to the sender, or it can go to some others in the group if they're caching messages, so you can get it from some other nearby node rather than all the way from the sender. But that's a detail. The more important part is you are going to send out a NAC, and then you are going to ask for that message to be retransmitted explicitly. As opposed to an ACK and a timeout, you essentially send NACs. Okay? So if you have a scenario where the network is only dropping messages for a small subset of your nodes, a NAC-based scheme will be more efficient, because for every message, you will only get a small number of NACs as opposed to a large number of ACKs. Okay? So that's more efficient. If you have a really lossy network, then this problem is not going to, the NAC is not going to solve anything, because you may get lots of NACs every time you try to send them. But we assume that the network by and large is well behaved and only occasionally drops packets. In this case, a NAC-based scheme will be a lot more efficient than an ACK-based. Yes, question. Okay. Yeah. The question is, are you queuing the messages at each of the receivers, and you deliver them in the same order? And if you know you missed it, can you not ask someone else? Right. So all of this is true. The way either TCP would work, or even in this case multicast would work, you are going to deliver messages in order. Okay? Because we will assume that network can sometimes even reorder messages and things of that. So you will essentially not deliver messages to applications out of order. You're not going to deliver message 22, and then you go deliver 19 and 23. They're arriving out of order. You keep a buffer in the operating system. Okay? All of this is actually happening in the OS, not at the application. Messages come in, you look at the sequence number, you order them, and so long as they're arriving in order, you deliver them in order. Okay? So if you have received 23 and then you receive 25, you don't deliver 25 and wait for 24 to come later. You will essentially buffer 25, okay? Send a NAC, request 24, wait for 24 to come, and then now you have all of the messages in order. Then you will deliver 25, 4 and 25. Okay, that's the first thing. The second thing, who can you ask for 24? As is shown in this example, okay, you can send a NAC back to the sender. The sender is already buffering, so that's why there's a buffer history that is keeping a buffer of all the messages, so you can resend the messages if NACs are received. Okay, that's number one. Second is, you don't only have to send that NAC to the sender, you can send it to the sender and some subset of the receivers if the receivers are closer to you than the sender. Then the lost message comes back faster than asking a faraway server to resend it to, which is why you will see in this figure, the NAC is actually going to the entire group of receivers as well as the sender. You don't have to send it to everyone, but in this simple example, it is being sent to every other node saying, if you have message 24, send it. Okay, so both of those things will be true for efficiency reasons. Okay? There's only one problem in NAC-based scheme, which is you send the final message in a sequence. Okay? There is no message after that to get a NAC. Okay? So you might have to add a dummy message after your last message just to make sure you get NAC for the last real message, so you can actually send the NAC. Okay, is that clear? All right. So we'll talk a little bit about various facets of multicast before we get to distributed commit. So what I showed you was a very simple multicast based approach, that is just sending messages, getting negative acknowledgements, and retransmitting lost messages and so on. But there are many properties sometimes you might need on your broadcast on multicast messages in addition to resending lost messages. Okay, and one is to ensure that you have ordered delivery. Right? So that is essentially called FIFO broadcast or FIFO multicast, which simply says if a single process sends M1 and M2, then all other processes should receive M1 before M2. Okay? So some of this you can reorder in the OS buffer because you're sending them in sequence numbers, using sequence number. You can order them and make sure you deliver them in order and so on. But if you have actually a multicast library that ensures this for you, then you don't need to worry about does the OS deal with it all. Okay, so you can have these systems that actually guarantee you FIFO delivery. Okay, that's the simplest one. The more complex one is totally ordered delivery, which says that if a process receives M1 before M2, okay, then other processes also receive M1 before it. Okay, because those are that basically those get ordered. So essentially, total ordering is harder because now you're trying to order messages across processes. Very similar to how Lamport's clock was trying to order events across processes. Okay, so in some sense, we are saying if two messages have an ordering on them based on, let's say, Lamport's clock or Vector's clock, you want to make sure that those messages are delivered in that order to all the processes. Okay? And that kind of is also mentioned here. Causally ordered, totally ordered says everything as a order, which is much harder. But causally ordered says if send of M1 happened before send of M2, these are two messages that are ordered explicitly using causal relationship or the happened before relationship, then the receive of M1 also has to happen before receive. You sent one message before the other, that message has to be received before the second message. Okay? That's a much harder property to guarantee, because if you imagine in the internet, message delays can be arbitrary. Okay? So you will have to have additional information to know what the ordering was, buffer them for extra amounts of time if you get them out of order, okay? Because you're not ordering by sequence number. So you're imposing additional ordering conditions on message delivery, which is saying there's causal relationship between messages and enforce those causal relationships. Okay? And then many others. Okay? So there will be a whole slew of this. We'll talk about one or two examples in the next couple of slides. Okay? The first one is called atomic multicast. Okay? So atomic multicast is a property that guarantees you atomicity on top of everything else. Okay? What does atomicity mean? If I send a message to a group, okay, either all the processes in the group receive the message or no one receives the message. Same as transaction. If you remember, transactions had an all or nothing property. Everything in the transaction either executes or nothing executes. You can't have half the code in the transaction execute. That thing doesn't exist when you're transaction. Same thing is true here. Okay? In atomic multicast, you are going to guarantee that every process in your group has gotten a message or no one. So if some subset of them get the message and someone else crashes, you have to essentially throw that message out and make sure that you undo the delivery saying nobody received. So you can't have a case where some half of them or 80% of them receive it. Okay? So this is important because we have things like replicated databases. Remember replicated databases, I gave that banking example. If you had an atomic multicast, okay, so you basically send a query, either every replica gets the query and executes it or nobody gets it. Okay? So this ensures that you don't have a case where some replicas have gotten a transaction and executed, others have not executed. So it's an all or nothing property that you will get. Okay? Now, that's just an idea. The question is, how are you going to implement atomic multicast? It's a complicated problem. Okay? So there's multiple approaches, but that's one we are going to look at it here, which is called the group view approach. Okay? The idea here is the way you are going to enforce all or nothing property is to actually track whether the group membership has changed, has some process crashed or disappeared in the group. Okay? So long as the group is static, okay, the network using TCP can deliver your message successfully. Okay? So you get the all property. But in the midst of delivering a message, if some process crashes, okay, you will have what is called a group change or a view change. Say that now the group membership has changed, there's one process disappeared. So then you got to track that and make sure that you will actually undo the delivery of that. Okay? So you are essentially going to have to add a layer on top of multicast which says, I'm going to track group membership. Okay? And group membership cannot change while there is a delivery of a message in progress. Okay? So if there's a process changes, the group changes during a delivery, then you are going to undo the delivery of that message. Okay? So you will see here that one process crashes, so the group has changed. Okay? So either in that case, you undo the delivery of the message, you resend the message with the new group if you want, and then that will go to the new group and so on. Okay? So this requires you to have this notion of tracking which processes are present, make sure the group changes are done in a reasonable way and so on. Okay? There is a system here that implemented it. Okay? The name of the system is actually ISIS, unfortunate name. The name was actually designed well before anything that you heard of ISIS, but that's what that system is called, which implemented this whole idea. Okay? So you will see here that same example I mentioned. So there's a group of 7 processes. Okay? One of them crashes. Okay? Process 4 observes it and says that there is a change of group membership. It essentially broadcasts that change, which may cause unsent messages to be flushed. Okay? And then once the group is stabilized in that, you say, now this is the new group. Then if you agree with that group, then you can start broadcasting to that smaller group, or you will have to wait until the process recovers. Yes, question. Okay. Question, how do you know which processes are present and which ones are not present? So this requires you to implement all kinds of things underneath which detects process failures. Okay? And so you will have to send what are called heartbeat messages or other techniques to know, am I alive messages, or are you alive message, not am I alive message, are you alive messages saying, is the process up or not, to actually track which nodes are up, which nodes are down, whether node has recovered and things of that. None of that is being shown here. I'm just assuming that you can detect faults. Okay? These are crash faults, not Byzantine faults. So they are much easier to detect. You can send your ping or heartbeat messages. If you don't hear back, you assume process crashed, group change. That's going to be the same thing you do for your lab, incidentally, right? You have to, in lab 3, you have to have fault tolerance. So you have to detect when a process has gone down, okay, on a replica, and make sure that you can then send the message to other replicas and so on. Okay? So yes, so there's also the details here that we are glossing over. Okay? But the higher level idea is you've got to track processes which are up and down, and then make sure you track this group changes. Okay. All right. So I'm not going to go through this table here, but all I wanted to show with the table is multicasting comes in many different flavors. Okay, and we only looked at 2 or 3 of these today. We talked about reliable multicast very briefly, which is very simple, which says I just want to make sure when I send a message, everybody gets it and I can retransmit message. It does not guarantee any ordering property. Okay? All it's doing is it's making sure that any packet losses you can deal with by retransmission using NACS. Okay? But then all of these other ones, okay, or the ones in the middle, FIFO, causal, okay, so those actually impose an ordering on top of reliability. So saying that you want to deliver messages in a certain order, in addition to making sure the messages get there, you want to impose an order. Okay? Atomicity adds one more property on top, saying not only do I want to make sure that messages are delivered in a certain order, I want to guarantee an all or nothing property on every send. Okay? So I don't want a case where some process crashes and the message does not get delivered. Okay? So that's stricter than the other two. And then there are, of course, different flavors of atomic multicast, which I didn't talk about. You can do FIFO atomic. So you have ordering and atomicity guarantees combined. Okay? So many different flavors gets very complicated. We are not going to deal with most of this. You have the basic idea. I think that's enough for the course. Okay? All right. So I'm going to now talk about the last problem briefly. Okay? We'll continue this in the next class. We won't be able to finish everything here today. Okay? But I'll introduce this problem of distributed commit. Okay? So distributed commit generalizes the problem of atomic multicast, where we were trying to do all or nothing. Okay? So there are many scenarios where a group of processes in a distributed system must either all perform an operation or no one performs the operation. That's a nice property to have if you want to maintain consistency or you have replicated databases and things like that. Okay? So reliable multicast was just one example where the operation you are concerned about is the delivery of the message. Either everyone gets that message or no one gets it. That's the operation you cared about. But you could think of many other scenarios, and we already looked at another example, which is distributed transactions, where either all the replicas do the transaction, none of them. Right? So there will be many cases like this where you want an all or nothing property on an arbitrary operation. What the operation is, we don't care about. Okay? It's some operation, and either all the processes in the group have to finish or no one finishes. You can't have some processes doing it or others no. This problem is called distributed commit, where the commit says that everybody agrees to have finished that operation successfully, and you want to do this in a distributed manner. Okay? So how do you solve the problem of distributed commit, where we have agreement on whether everyone has completed that operation, and if there's no agreement, then you essentially undo and abort. Say that nobody, so undo whatever you did. Okay? Similar to how you did this in transaction. Now the operation is no longer just a transaction. It could be any operation that you want to use for distributed commit. Okay? So we'll look at 2 techniques. Okay? Today we are going to look at 2-phase commit, okay, called 2PC. Okay? And then next time we are going to look at 3-phase commit or 3PC. Okay? Do not confuse 2-phase commit with 2-phase locking. Okay? When we did concurrency control, there was some locking techniques we talked about, which was called 2-phase locks. Okay? Here we are talking about 2-phase commit. The word 2-phase appears in them, but they are completely different concepts. So they just have 2 phases in what they do, which is why they are called 2-phase locking or 2-phase commit. But beyond that, there is no real similar relationship between them. Okay? So here we'll talk about the problem of distributed commit, and we'll have 2 rounds, which is why it's called 2 phases. And then in 3-phase, you'll say there are 3 rounds to actually get to commit. Okay? So the 2-phase commit, the technique is actually fairly straightforward, but arguing for correctness, saying that no matter which process crashes, what happens, we still get to a correct state, a little bit harder and more involved. Okay? The book actually has a textbook as a 2 or 3-page description of it. You should go and read it if you want to know about that in more detail, but I'm going to explain the basics. Okay? So the understanding the process is very simple. There are 2 phases or 2 rounds in which we are going to figure out whether to commit an operation or undo the operation. Okay? So essentially, we'll start with a coordinator and multiple nodes. Okay? The coordinator is simply going to ask everyone to vote, should we commit or not commit? Everybody gets to vote. Okay? So the coordinate sends out a vote request saying, do you want to commit this operation or not commit the operation, or abort the operation? Okay? So you get all the votes back. If every node says commit the operation, then you say, okay, we'll commit the operation. Okay? If even one node says abort the operation and everyone else says commit, that's a veto. Okay? Because one node says it could not finish the operation successfully, it wants to abort, so then everybody has to undo. Okay? So if the vote result has a single abort, then one or more aborts, you abort. If everybody says commit, you commit. Okay? So in round 2, you are then going to then tell everyone what the results of the vote was. Okay? So that's the basic idea, but here is how it's going to work. Okay? There are some diagrams, figures here. Okay? You will see what is happening is this is the coordinator. Okay? These are other nodes, and there's a timing diagram that actually shows what is happening. So the first phase, you send a vote request, okay, and then ask for the results of the vote. So you start from the init. So this is a state transition diagram. You start from an init state, and then you ask for whether you want to vote or not. Okay, and then you go, and the coordinator is going to go into a wait state. Okay, then you wait to hear what to do, and if you essentially get and vote for an abort, then you basically go to the abort state, and everybody is going to abort. If everybody is voted to commit, you're going to the commit state. Okay, so here is essentially a state transition diagram of any node. Okay, that was the coordinator. Okay, this is a node. The node is also initially in the init state. If it gets a vote request and it votes to abort, you can make a direct transition to abort. You know what the outcome of that vote is going to be, because you already voted to abort. Okay? But if you vote to commit, you go into a ready state and you wait, because you don't know what others have actually voted for. So you need to wait for the results of the election before you can decide what to do locally for your operation. Okay? And if the coordinator tells you to abort, you are going to send an abort. Coordinator tells you to commit, you are going to commit. So if you think about it, it's a very simple process. The coordinator asking everyone to vote based on the results of the vote. It tells everyone what to do. Okay? And each node, all it has to do is it has to wait for a request from the coordinator. It votes abort or commit. If you vote for abort, you know what the outcome is. You can directly abort without even waiting for the vote results. But if you vote to commit, you got to wait to hear the election results, and then you commit or abort depending on the outcome. Okay? Yes, question. Yes. So the problem is that we got to discuss is what happens. I will not look at the code right now, but that's exactly the issue. Because this is a distributed commit and you have an all or nothing property, you can never have a case where some process has crashed and you have made a decision where some other processes end up in commit and someone else ends in abort. This can never happen. Then you don't have an all or nothing property. So put another way, this very simple two-phase voting protocol has to always end in a consistent state, no matter who crashes at what state. Coordinator can crash at any time. Okay? Processes can crash at any time. Okay? And you can't actually do anything in that case. So we got to analyze what can happen in this. So we'll actually take a look at the coordinator and says what happens when it crashes at each of these stages and so on. Right? So in some sense, the problem with two-phase commit is if all the processes have voted and then the coordinator crashes but never sends the election result out, okay, what do you do? Okay, you could say, why not just ask all the other processes what they voted for and then decide what to do, which is the same as saying maybe you elect another coordinator. Okay? But you can't actually do that because a coordinator is also a process that voted. You don't know what it voted in that for this operation. So if you don't know what it voted, you can't actually make a unilateral decision without that coordinator's vote as well. Okay? In that case, the coordinator is voting for itself, but doesn't send the vote request. So if the coordinator crashes, okay, there are only a few things you can do. Okay? So if what you can do is, if the coordinator crashes, you can ask other nodes. If one of the other nodes has actually reached an end stage of a commit or an abort, you can still make a decision, because if you find a process that's in the abort state, you know that it has actually voted for an abort. That's the only way you will end here, right? So then you know, or you know that some other process actually voted for an abort and this process got a vote result from the coordinator, it went to an abort. Regardless of what it is, you know that it's safe to abort and everyone else can abort in this case. Okay? Similarly, if you find even one process in the commit stage, okay, commit end stage, what you can infer from this is the coordinator got all the results, okay, and it essentially all the results are to commit, and it started sending election results out, and at least this process got the outcome of the election, and maybe other processes didn't, and the coordinator. So now you at least know what the election result was, and other processes can commit. Okay? So when the coordinator crashes, if you find at least one other process in the commit stage or the abort stage, it's safe for everyone else to actually take that same decision. Okay? But the problem will arise if the coordinator crashes and everyone is stuck in the ready state, where you voted on the outcome of the election, but you don't know what the outcome is. In this case, it's not safe for any of the processes to make a decision without the coordinator, because remember, the coordinator is also a voter in this case. So you can't say, what did you all vote? And then you are taking an election result with n-1 processes and ignoring what the nth process wants to do. Because if you all say commit and that coordinator wanted to abort, you will end up in a wrong state because the coordinator may itself have decided to abort. Right? So you don't want that. So if you are stuck in the ready state, two-phase commit is deadlocked. Okay, this has a deadlock problem. You cannot make progress because you don't know what to do. Okay? But if the coordinator crashes, but you find some other process at one of the end stages, you can make progress. But two-phase commit has this deadlock problem. Okay? The question is, can you not discard the coordinator and elect a new coordinator and continue? You can do that, but you cannot figure out what to do with this operation. You can do that for all subsequent operations, because then the coordinator is crashed, not participating in any result. So there's no risk of it making an incorrect decision. But the question is, what do you do for this operation? So you're deadlocked for this operation. You can continue for other operations. Right? So you can say, we leave out the coordinator now, n-1 processes can agree. That's okay. But the point is that for this operation, you will still be deadlocked until the coordinator comes back. Is that clear, what I said? Okay. So this has actually quite a few subtle things. This is the code of the pseudo code which you can look at. It's basically the two-phase voting, as you will see, that you essentially decide what the vote is and you send out responses and so on. I will not go into this because I explained what this is, but here is essentially what I was talking about. Okay? So if you actually essentially is if you're in the ready state, okay, and you're not heard from the coordinator has crashed, you can contact some other process Q, and depending on its state, you may or may not be able to enter the final state. So if Q is in the commit stage, as I said, you know that Q received a vote from the coordinator to commit a result, so you can commit. Q is in the abort state, you know that the decision is to abort because at least Q has voted to abort, or Q has received an election result abort, you can make it. If you're in the init state, you know that you haven't even voted. Okay, so init is basically you haven't even started. So in this case, there is no way the coordinator can make a decision because you know you have not voted. So in this case, also it's fine to abort, okay, because you can essentially tell abort and have everyone else abort. But if you're in the ready state, okay, and the other process is in the ready state, you have to keep checking. If everyone ends up in ready, then you are deadlocked. Okay, that was the scenario I just mentioned. Okay, so there's a two-phase commit. So it is safe in that if you enter a final state, everyone is guaranteed to be in that final state. You will never have a case where some processes commit, other abort, because that will not give you the all or nothing property. Okay, so you will always have that property, but okay, so that's called a safety property. Safety property says nothing bad happens, right? So you will not have a scenario where you make different decisions, but two-phase commit, because it can deadlock, does not have what's called the liveness property. Liveness property says something good happens, because in this case, you may all be stuck and you cannot make progress, so you're deadlocked. Okay? So safety property is not compromised. We'll not do anything bad, but you may be deadlocked and you can't make progress in the system either. Okay? So we can talk about the three-phase commit protocol that tries to address this coordinator failure problem. but we will start talking about that next time. Okay, so we'll stop it here today and then continue with three-phase commit, and then we'll also talk about consensus using Paxos and Raft next time. Right, so let's stop.